Hello everyone, welcome to Dakshana e-classroom program. So today we are going to discuss the solution for DT07 NEET paper part physics. So let's continue without any delay. I hope everyone tried their best and you must have got your score also and let's see if you are still having any doubt regarding any question. I hope like this video will make that clear for you people. So let me start with question number 1. An electron accelerated through a potential difference V passes through a uniform transverse magnetic field and experiences a force F. If the accelerating potential is increased to 2V, the electron in the same magnetic field will experience. So here, see, this is question number 1. So electron accelerated through some potential difference V, so it means it's gaining a kinetic energy half mv square, and we are getting V is equal to under root 2qv divided by m. Let me write this is V naught potential, accelerating potential, and magnetic force is given by qvb. Right now it's saying next case, if V naught is made to 2v naught, I am taking the potential difference as V naught, then what will happen? The velocity will become, speed will become under root 2q into 2v naught divided by m, and then f prime will be q v prime into b. So you can see f prime is directly proportional to v prime, and it has become, this is equal to what basically, so you can write simply, just simplifying, f prime is equal to root 2 times of f. So your answer matches with option 3rd. Next, question number 2. An electron is moving along positive x-axis. So electron is moving along positive x-axis. This is electron moving along positive x-axis. So V I cap. After being accelerated to get it moving in an anti-clockwise circular path in XY plane, a magnetic field. So anti-clockwise, we want the electron must be accelerating in this direction, right? So now what should be happening? Like the magnetic force must be acting at this point, it must be providing circular force, so this should be the magnetic force, and we know F magnetic is equal to what? Q. This is V bar cross B bar, right? So we know already the direction of magnetic force, and that we can write actually V bar cross B bar. So like in this direction we want it upward, so you can simply get it from here. So velocity, okay, so we want magnetic field should be, so that the force should be in this direction, is it? So the force will be in the direction of thumb, so I am already getting it in this direction. I will align my fingers in the direction of velocity V cross B, so that thumb will give you V cross B. If you are taking your fingers in the direction of first vector, curling towards the direction of second vector, then thumb will point you or give you in the direction of third vector. So I know the third vector direction, I know the first vector direction, I just need B bar, so that I am getting resultant here. Remember that it's minus q because charge is negative, so it should be we should be taking care of that too. So now see, if I am taking force in this direction, velocity in this direction, then magnetic field should be inward, then it should give you upward. But because it's negative charge, negative, so what it should mean, the force should be actually acting this way, but negative will make it upward. So then V cross B, so it's coming downward force, but it will make it, because negative sign, so that means magnetic field should be outward. So magnetic field we can write along negative y direction, no, along negative, no, it's along positive z direction. Your second answer will match here, question number 2. Next, question number 3. Two particle x and y having equal charges. So both particle x, y having charges equal. After being accelerated through same potential difference, V naught, okay, difference, enter a region of uniform magnetic field and describe radius of circular path R1 and R2. In R, we know actually it's first thing is this is the accelerating potential, and their masses are given, let's say M1 and M2, okay, and it's ultimately enter a region of uniform magnetic field and describe circular paths of radii R1, R2, respectively the ratio of masses of x and y. So it is asking the ratio of, so we need to actually connect the radius finally r1 r2, we need to connect the radius with the masses, then we will rearrange and we will get the answer. So first thing is we know actually r is equal to what, mv by qb, but we have q because it's given same. B, magnetic field we can take also b, and mass m1 we can take, and velocity is equal depending on v naught. So we can write v, velocity v1 will be equal to under root q v naught divided by, this is 2q v naught, this is v1 equal to q v naught divided by m1. Similarly v2 will be under root 2q v naught divided by m2. So this implies r1 I can write m1 by qb under root 2q v naught by m1, right? Similarly r2 will be, or I can rearrange it also a little bit, then r1 will be, this is remaining things I am just keeping it 1 by qb and under root 2q v naught into m1. Okay, let me write it. This is r1. R2 similarly I can write 1 by qb, this is under root 2q v naught into m2, right? Then this implies just from here I can write r1 by r2 is equal to what, rest remaining things will cancel out, it's simply under root m1 by m2, and this implies m1 by m2 is equal to r1 by r2 whole square. So this will be the answer, and which matches with r1 by r2 whole square, matches with option 3. So that is question number 3. Next, question number 4. A charged particle of mass given, so mass of the charged particle is given as 10 to the power minus 3 kg, and charge given q is equal to 10 to the power minus 5 coulomb. Okay, enters a magnetic field of induction B is equal to 1 Tesla. If g is given as 10 meter per second, for what value of velocity will it pass through the field without deflection? So you should be like, this is one of the application of velocity selector. So in this case what is happening, one is gravitational force is acting, another if magnetic force is exactly opposite of the gravitational force. Here you are not supposed to bother about the direction of magnetic field, it is automatically settled in a manner such that it is exactly cancelling out. So particle moving here, mg is acting downward, then magnetic force must be automatically like acting upward, that will cancel out. So we just need to balance it. So mg, m we know 10 to the power minus 3, g is 10, should be equal to what, q is 10 to the power minus 5 into v, velocity, it's okay, for what value, okay, it's asking v into b is 1 Tesla, right? So just simplifying it, we are getting v is coming out to be, it's 10 to the power minus 3, so it's 10 to the power minus 2, then it's like okay, 10 to the power like 1000 meter per second, or you can write it that's equal to v is equal to 10 to the power 3 meter per second. That matches with option number 2. So that is question number 4. Next question number, a charged particle move along circle under the action of possible constant electric and magnetic field. Which of the following are possible? So in which of the following case a particle can move in a circular path? Electric field 0, magnetic field 0, charged particle definitely like no electric field, no magnetic force, then who will provide the required centripetal force? So definitely not possible. Electric field 0 and B is non-zero, definitely yes, it can possible. Which of the following are possible? Okay, and E is non-zero, B is 0, in that case also it does not happen actually. E is 0, so like here 2 will be the, so that next is question number 5, 2 is the best possible answer, we know actually. So it's just talking about possibility. In fourth case, sometime like there is possibility of helical path, but not exactly circular path. Next question number 6, a proton and alpha particle enter a uniform magnetic field moving with same speed. So one is question number 4th, proton, and another is alpha particle moving with enter uniform magnetic field moving with same speed, v speed, and if proton take 25 microseconds to take make 5 revolution, then the periodic time of alpha particle will be, so first is time period is given by 2 pi m by qb. This is the time period, so means which is actually independent of even like their velocities, and it's also given velocities are equal. So time period is depending on 2 pi m by, because t is equal to 2 pi, which is constant, divided by b is also constant, m by q. So it's given time period for uniform magnetic field moving with the same proton take 25 microsecond to make 5 revolutions. So means for one revolution I can write it will be 5 microsecond. 5 microsecond per, this is equal to 2 pi by b. Mass, let's say if I take mass of proton is m and charge is q, then this is the condition. Next case, let's say time period is t for alpha particle, then it will be 2 pi divided by b multiplied by mass of alpha particle is 4m divided by charge is becoming 2q. Just simplifying it, dividing it, rest everything cancelled out, and we are getting 5 by t is equal to 1 by 2. This implies t is equal to 10 microsecond. 10 microsecond, this is microsecond for per revolution, you can write. We need to check what it's exactly saying. Okay, so then the periodic time for alpha particle, yes, it's asking about periodic time, so that will be 10 microsecond, and that matches with option number 3. So let me raise it just. Okay, next question number 7. An electron is launched with velocity v bar in a uniform magnetic field b bar. The angle theta between v and b lies between 0 and pi by 2. Question number 7. So v bar velocity, b bar magnetic field, and theta angle between these two lying between 0 to pi by 2. First thing is, if it is 0, it will be like path will be straight line. If it is exactly pi by 2, path will be circle. And we know when the angle is lying between this, then it is helical actually path. And in helical path, we know the time period is given by actually 2 pi m by qb, because it's asking, okay, its velocity v bar return to its initial value in a time interval of, all right, so velocity, it's asking like its velocity vector v bar return to initial value in, okay, so yes, here time period we know, and let me explain it a little bit more. So in this situation the path is helical, and exactly if it is like, let's say starting from here, then exactly it will be in similar situation exactly after one time period, and time period in this case of helical path also it's given by 2 pi m by qb. That's so simple, straightforward formula based question, and option will be like 1 for question number 7. Next question number 8. A charged particle is wheeled in a horizontal circle on a frictionless table by attaching it to a string fixed at one end. So charged particle, let's say it's wheeled like this, actually with some angular velocity attached to a string and T is some tension. If the magnetic field is switched on in the vertical direction, so magnetic field is in vertical direction B bar, okay, in the vertical, the tension in the string. So now remember that actually it's not mentioned that charge is plus q or it's minus q, nothing is given, right? So at any moment of time, let's say the velocity vector is v, then I can write force on this charged particle is v cross b. If the charged particle will be positive, force will be in this direction, tension will increase. If the charged particle is negative, then it will be just opposite and tension will decrease. So because it's not mentioned the charge on the charged particle is positive and negative, so may increase or decrease. Remember, a charged particle is wheeled in a horizontal circle on a frictionless table by attaching it to a string fixed at one end. If the magnetic field is switched on in the vertical direction, the tension in the string, so if charge was supposed to like mentioned, then definitely we could have answered it will whether it increase or decrease. Because charge is not mentioned, that's why it may increase or decrease. So answer will be like fourth, depending on the charge on the particle. Next question number 9. A particle with a specific charge is fired with speed v towards a wall at a distance. Okay, so wall at a distance, so like let's say charge q and mass m, and this is the specific charge. Let me write it some alpha. All right, fired with the speed v toward a wall at a distance of d. So this is the distance d, and a perpendicular perpendicular to the wall, what minimum magnetic field must exist in the region for the particle not to hit the wall? So minimum like B must be there. Like what will happen actually if the particle is either turning this way or it's turning this way actually, so that like it will be describing ultimately a circle, and if it is going just tangential at the just before the wall, then there is will be no possibility of hitting the, so means I can write means the radius must be should be equal to actually d, and we know r is given by mv by qb, and mv this is given as, okay, it's actually given as not alpha, it's given as a specific charge as s. So we got actually, and r should be equal to what, d, and this should be equal to what, q by m, so it's v by sb is equal to d, and this implies b, just rearranging for, it's v by sd. So that option matches with like answer matches with option 1. Next question number 10. A charged particle begin to move from origin in a region which has uniform magnetic field in the x direction and uniform electric field in y direction. So magnetic field in x direction, electric field in y direction. This is x and this is y, and charged particles start begin moving from origin. All right. Okay, so which has uniform magnetic field in positive x direction and uniform electric field in y direction. Its speed is v when it reaches the point x comma y comma z, then v will depend. Okay, so let's say at some point of time like movement here x y z is the coordinate, then its speed become v. Okay, charged particle begin to move from the origin in the region, okay, which has uniform magnetic field, okay, in the x direction and a uniform electric field. So now you must be understanding here in which direction the acceleration will be there, I mean like the force, because this cannot accelerate it, I mean it cannot change its speed. The force due to magnetic field cannot change the speed, it can just make it to revolve in a circular orbit, that's the only possibility. So only this will be the reason for changing the velocity. So we will depends only on electric field, means it will depends only on x direction, so only on x direction will be the first option. Like simple thing, magnetic force doesn't do any work, it's all right, just 1 second, it's okay, yes, it's saying it's a speed. If it is asking about velocity, then things might be different actually, because velocity it will be like making different is it the path will be like sort of helical, so it will depend exactly on like all factors. Velocity, because direction we need to consider, so here it's talking about speed, so only it will depends on x component. Just 1 second, electric field is in y direction, so it will depends on y direction, that is option 2. An electron moving with speed u along positive x-axis at y is equal to 0 enter a region of uniform magnetic field which exists to the right of y-axis. Next question number 11. The electron exits from the region after some time with a speed v at coordinate y. Okay, so here just see it, electron, it's talking about clearly electron. Okay, so charge will be negative and mass some, and magnetic field is in inward. So first thing is, what will be the force on this charged particle? So it will be like v cross b. If positive charge, then force will be upward, but because it's negative charge, so force will be downward. So the electron will have path something like this. If magnetic field is somewhere here, then it must be crossing here, the region of magnetic field. So we can definitely say, because speed doesn't change in case of magnetic field, so v will be equal to simply u. So we will have either 2 or 4th option, and next case y coordinate will be greater than 0 or less than 0, it will be less than 0, so 4th will be the right option. Next question number 12. All right, a particle of charge q and mass m start moving from origin under the action of electric field. Okay, so charge q, mass m, charge particle having electric field E is given as E naught I cap. E is equal to E naught I cap electric field, and B is also equal to B naught I cap, both are in I cap, with velocity v is equal to v naught j cap. Velocity is in j cap direction. The speed of the particle will become 2v naught okay after time t. So here the thing is that speed will change because of work done by electric field, is it? So it's talking about the time actually. So first thing is I can write the change in kinetic energy will be equal to work done by electric field, is it? So I can write work done by x into q into E naught will be the work done by, because this is the force multiplied by x, only displacement in x direction will be the basically responsible for work done by electric field. So this should be equal to change in kinetic energy half m, final velocity is becoming 2v naught whole square minus v naught square. So this implies x is coming out to be 3m v naught square divided by q e naught into 2. This is the displacement, and it's talking about the speed of the particle will become 2v naught after time t. Okay, so all right, so what is the, this is the, I mean like displacement, and acceleration can be written as a is equal to q e naught divided by m, and we can write x is equal to what, initial velocity 0. All right, initial velocity it's given as k, so we can write it x, right, just 1 second. So this initial velocity is v naught into t plus half, it's talking about, just 1 second, we check the calculator. Okay, just one thing. So we got actually like by conservation of energy, this is the work done by electric field, and that will be equal to change in. So I got the displacement by the time the velocity in like velocity will become 2v naught, or you can say speed will become 2v naught. So we got, this is the displacement, it will be covering in x direction, and initial velocity I will write vx is given as 0 actually. So it will be like simply ux, let me write it simply ux, that is given as 0 into t into ax into t, and acceleration in x direction is simply this. Then by using this is equal to 3m v naught square divided by 2q e naught is equal to ux 0 plus half ax is equal to q e naught by m multiplied by t square. 2 gets cancelled, q e naught m, so t is coming out to root 3m v naught divided by q e naught. This will be the answer which matches with option number 4th. So this is up to question number 12. Okay, next question number 13. A conducting rod of mass m and length l is placed over a smooth horizontal surface. So let's say this is the situation given. A uniform magnetic field B is acting perpendicular to the rod that I have taken inward, which is perpendicular to the rod. A charge q is suddenly passed through the rod and it acquire an initial velocity v on the surface. The q is equal. So let's say q is passed in time delta t. Then equivalent current I can write that is equal to q by delta t. This is the equivalent current. Then force acting on the rod can be written as ILB, that is equal to I is q divided by delta t multiplied by L into b. This is the force. Impulse is given by force multiplied by time interval for which it is delta t, and that is equal to QLB. And this I can write change in momentum. Initial momentum 0, right? Final momentum I can write some mv, so QLB is equal to m into v. This implies it's talking about q, so q is equal to mv divided by lb. That matches with option number 3rd. This is the answer. Question number 14. Two identical particles having same mass and mass m and charge plus q minus q separated by distance g enter a region of magnetic field B directed perpendicular to the paper involved with the speed v1 and v2 shown in the figure. The particle will not collide if. So here what is happening, like basically there is a region magnetic field and one particle entering here charge minus q, another charge particle plus q, and so what will happen actually, force on this particle will be like v cross b, so it will be like negative charge particle. Inward downward it will be moving like this, and another charge particle, let's say here, so that will be this way. So if what will happen actually, now it's saying, all right, just one second. Okay, B is directed perpendicular to the plane separated by distance d. Okay, enter a region of magnetic field B directed perpendicular to the paper inward with a speed v1 and v2 s1. The particle will not collide if d. So here what will be the r we know radius is equal to what, mv by qb. So charges are equal, so r can be written as basically m, and velocities are also equals v1 by qb. Similarly r2 can be written as, that is equal to m v2 divided by qb. Now the condition for their collision, I mean like not to collide, is okay, is that, see, if like maximum what will happen actually, this will be like diameter, right? Diameter I can write 2r1. Similarly diameter for this will be like 2r2. So if the separation between them is greater than 2r2 plus 2r1, then there will be no probability of collision, right? Definitely, or no possibility of collision. So we can write the d must be greater than like 2r1 plus 2r2, and I can write d must be greater than 2r1 plus r2, just writing it, m v1 by qb plus m v2 by qb, and that you're just rearranging, you will get it's matching with option number 3. That is question number 14. Next question number 15. So here magnetic field in a certain region is given by b is given by, it's 40 I cap minus 18 k cap. This is Gauss. How much flux passes through 5 centimeter area? So A is equal to 5 centimeter square, that can be written as 5 into 10 to the power minus 4 meters square. This is the area. We know phi is equal to what? B dot A, is it? And in this situation it's a XY plane, the area loop in this region, okay, if the loop lies flat in the XY plane. So loop is lying flat in XY plane, that means this area vector will be what? K cap, will be along K cap. Then flux is this, and so both will be like, this is minus K cap because flux due to this will be 0. So I can write phi, this is equal to minus 18 multiplied by 5 into, this will be like Gauss meter square, 5 into 10 to the power, like, just one second, 10 to the power minus 4 Gauss meter square, and Gauss we need to convert that into Tesla. So 1 Tesla is given at 10 to the power 4, so means 1 Gauss is equal to 1 by 10 to the power 4. So just changing that, it comes out to be like minus 90 into 10 to the power minus 8, and that can be written as phi is equal to minus 900 nano, is it Weber, or whatever the unit it's given, yes, Weber. So that matches with option 1. Question number 16. Okay, charged particle enter a uniform magnetic field with velocity vector v at an angle 45 degree with the magnetic field. So let's say magnetic field is in this direction b, and charged particle enter with 45 degree velocity. So what will happen? It will, this is the velocity, it will have one component in this way, another component in this way. This is v by root 2, and this is also v by root 2 meter per second, right? Now see, okay, the pitch of the helical path followed by the particle is p. So first thing is, what is pitch? Pitch can be written as, that is okay, first just time period is equal to 2 pi m by qb, then pitch is equal to time period multiplied by velocity, that is v by root 2. So pitch can be written as basically 2 pi m by qb multiplied by v by root 2. This is pitch. Now it's talking about the radius of the helical path will be, so radius will be because of only this component, and we know r is given by mv by qb. So just substituting r is equal to m, v can be written as v by qb multiplied by root 2. So this is r, and pitch is this actually. So just I need to So here mv by this quantity is equal to what? R. So then, all right, I can write 2 pi. This is 2 pi r is equal to p, and this implies r is equal to p divided by 2 pi, and that will be matching with option 3. So answer to question number 16 will be third. A loop of flexible conducting wire of length L lies in magnetic field which is normal to the plane of the loop. Current I is passed through the loop, then the tension developed in the wire to open up. Okay, question number 17. It's a good question. So here what is happening? Loop is lying like this, and there will be magnetic field, and some current is passing. So what we do here in this situation, we take small element angle d theta, and there will be like tangent. So this and this will be like d theta by 2. This will be also d theta by 2, and here if I take magnetic field is inward, is it, and let's say current is flowing in this direction, then force on this will be L cross B inward, is it, and that force will be like, I can write balancing the, this is tension T, this is tension T. I hope you are understanding this. I am taking, depending on, you can take B outward also. In that case it will try to open, so B will be actually outward here. Loop of flexible wire length in a magnetic field in which is normal to the, so it's given simply B is normal to the plane and it's trying to open, so means B should be actually outward, because if this is the situation, or otherwise current should be clockwise, is it, then it will be like trying to expand it. So in this possibility also it will be like expansion condition in loop. Now what is happening here? We will do, this is 1. So now T, we can take 2 component in this direction. So this is 2T sine d theta by 2. This will be the force, and these forces will simply cancel out. So I can write 2T sine d theta by 2 will be equal to I. L will be equal to R d theta multiplied by ILB. I hope clear with this. For small value of theta, sine theta can be written as simply theta, and 2 to cancel, d theta also again gone. Then we are getting T is equal to I into R into B, and it's given L is equal to 2 pi R. So R will be equal to what? L by 2 pi. Substituting, so tension is coming out to be ILB divided by 2 pi, and it's asking about only tension, so yes, it matches with option third. That is the answer to question number 17. Okay, next question number 18. A uniform current carrying ring of mass m and radius r, so this is ring of mass m and radius r, connected by a massless string as shown in figure. Uniform magnetic field B exists in the region to keep the ring in horizontal position, then the current in the ring is, okay, so here what is happening, basically torque due to mg, and torque will be like equal to, this is tau mg, which is trying to rotate it, trying to basically like tilt it downward, is it, and tau due to basically magnetic movement, I will write m, and magnetic movement is given as I into A, that is I into pi into r square, and that will be like acting, this is direction of m bar, is it, and magnetic field, and then tau is equal to m bar cross b bar, and that we can write m b bar I pi r square into b, and m cross p is, we can see actually its tendency is just countering opposite of this. So to keep this ring in horizontal, these two tau must be same, so tau mg must be equal to tau m due to magnetic movement. This implies I pi r square b must be equal to mg r. This r gets cancelled, and I is coming out to be mg divided by pi r b naught, and this is the answer to question number 18, that matches with option number 1. Next question number 19. A charged particle moving along positive x direction with the velocity v enter a region where there is a uniform magnetic field b naught minus k cap. So a charged particle, this is a like B naught minus K cap is the magnetic field acting, and charged particle is entering in this region here with velocity V, and it's describing some circle, and because magnetic field is limited only in some region, so it will be like describing only some angle theta. Now in this situation, this is given as D. So we can write, actually, if radius is r, then what it means, d is equal to what, r sine theta, and we know r is equal to what, mv divided by qb. So this implies I can write d is equal to mv sine theta divided by qb. So we got it up to here. Now it's asking the particle gets deflected at an angle theta. Okay, the specific charge of the particle, means it's talking about q by m. So that is the specific charge, and that will be equal to q by m will be equal to v sine theta divided by d into capital B. This is the specific charge that matches with option number 4. Question number 19. Next, question number 20. Okay, 3 particle, electron, proton and helium, are moving in circular path with constant speeds. So electron, proton and helium and moving in circular path with constant speeds. Okay, in a region where uniform magnetic field B exists along z axis, the time taken by electron to inside the field to complete one revolution, means their time period t is given by 2 pi m by qb. So t electron will be equal to 2 pi m electron divided by q charge into B, and the time period of proton will be equal to 2 pi m proton divided by EB, and time period of alpha particle can be written as 2 pi into mass of alpha can be written as 4 into mass of proton divided by charge is 2, so 2 E into B, and we can see it's directly proportional to mass, and here its mass is very less, so this time period will be definitely very small compared to this, and compared to this it's even becoming 2 times, just 2 times, is it, instead of this. So overall I can write T alpha is greater than T proton greater than T electron. That's the simple order of time period. Question number next, question number 21. It's saying conducting wire is sliding with constant velocity v along 2 parallel conducting rails as shown in the figure. The resistance of the conductor circuit is R and the magnetic field present in the region is B. If P1 is the rate at which energy is dissipated in the circuit and P2 is the rate at which work is done to move through the magnetic field. Okay, then in this situation you can see actually what is happening. Heat will be dissipated in resistor, and because on the wire a force will be acting, and to counter that basically we need to do some external work, and it's like no other dissipating system is there. So definitely we can write the P1 rate at which energy dissipated in the circuit must be equal to, because it's also given conducting with sliding with constant velocity, so means there is no change in kinetic energy, also velocity is also constant, so means kinetic energy will be also not changing. So in that situation, simply question number 21, it will be like P1 will be equal to P2, matches with the option 3. Next, question number 22. A particle of specific charge equal to, this is pi coulomb per kg, okay, is projected from the origin toward positive x-axis with the velocity of projected from origin towards the positive x-axis with the velocity of 10 meter per second, okay, in a uniform magnetic field 2 k cap. So this is B is equal to 2 k cap Tesla. This is the magnetic field. Alright, the velocity v of the particle after time. Okay, so first thing is, this is the situation, and charge is given as positive, so we can write the force acting on the particle will be like q v cross b, so it will be downward, so the particle will describe a circle, is it, like this, and some center will be somewhere here, and it's given actually the velocity v of the particle in time t, and t it's asking 1 by 12 second. Okay, so first thing is, let me just calculate how much angle it is describing. The velocity will be in this direction, and speed doesn't change. So initial speed is 10 meter per second. Then here also it will be 10 meter per second. If this is the angle theta, this will be like 90, this will be 90 minus theta, this will be also theta. Then this because this is total 90 degree, I can write, so this will be equal to, this is also theta, this will be also equal to theta, right? Okay, so then we can write it's a v cos theta, and this will be v sine theta. This is minus j cap and a cap. Okay, theta can be written as omega into t, and omega is given as, omega is equal to pi m mv, r is equal to mv by qp, to t. Time period we know this is 2 pi m by qb, so omega is actually qb by m. Okay, so by this we can get theta is equal to, basically theta is equal to omega into t. I mean this time taken 2. So just substituting the values, we are getting theta, let's say omega q is given as how much? Okay, q by directly, just one second, q, this is pi multiplied by b, and b is 2 into, this is t is 1 by 12, so this is given as pi by 6, right? And then just substituting this, v pi by 6, 30 degree, so it will be like 10 into root 3 by 2, 5 root 3 I cap, and this is 10 into sine 30, that is basically 5 minus a cap. So the velocity comes out to be 5 root 3 I cap minus a cap. Third is the right option for question number 22. Next, question number 23. If consider a hypothetical system, 23, spherical body. The body is cut into two parts and about the diameter. One of the hemisphere portion has a mass distribution m, while the other has its portion has an identical charge distribution equal to q. The body is rotated about the axis with a constant speed omega. The ratio of the magnetic moment to the angular moment. This is a standard question actually. We know L by magnetic moment by angular momentum, m by L, this is equal to q divided by 2m. So that will be also the answer in case of question number 23. Next, question number 24. A stream of electron is projected horizontally to the right. Question number 24. So stream of electron, let's say this is the stream of electron projected towards the right. A straight conductor carrying current supported parallel to the electron stream and above it. So there is a conductor carrying some current I, which is placed supported parallel to the stream and carrying current I, okay, and above it. If the current in the conductor is from left to right, so current is given from left to right, that is also, so then due to current carrying wire, the magnetic field in this region will be like what? By just right hand thumb rule, right will be inward. So this will be the B, and then we can get the magnetic, okay. If the current in the conductor is from left to right, then what will be the effect on electron stream? So let's calculate what will be the force or what will be the direction of force on electron stream. So we can write force is equal to what? Magnetic force Q V bar cross B bar. So if I just check the direction, this is V bar cross B bar, but electron is negative, so force will be like downward. So that means they will simply deflect away. So electron stream will be pulled upward, no, electron stream will be pulled downward, electron stream will be retarded, electron stream, so it's simply like second is the right option. It will be pulled downward, means away from the wire. Okay, so let's see next. Next, question number 25. A charge q coulomb move in a circle at n revolutions, charge n revolution per second, so then omega is 2 pi and time period is equal to 2 pi divided by omega, that is equal to 1 by n. Then radius of the circle is r meter. The magnetic field at the center of the circle, so this will be equivalent to one current carrying ring, and if I is the current, then I can be written as Q divided by T, that is equal to I is equal to Q into N, and B is given by mu naught into I divided by 2R. So B is coming out to be mu naught into I Q N divided by 2, and R is R, 2 pi multiplied 2 pi, so this is mu naught by 4 pi, that is so Q N by 2R, I mean like by R into 2 pi into 10 raised to power, this will be like minus 7 Newton ampere inverse meter inverse. So that will match with the 2 pi Q N, option third. Question number 26, this was 25. A circle current carrying coil has radius R. Circular current carrying coil has radius R. The distance from the center of the coil on the axis where the magnetic induction will be 1/8 of its value. So B at center can be written as mu naught into I by 2R if R is the radius, and at distance, let's say x from the B, at x is equal to mu naught into I into R square divided by, this is 4 pi x square plus R square power 3 by 2. So this is the B at distance, into here also comes like mu naught into I into, just 1 second. Okay, so actually this is mu naught into I, either it's 2 pi or I can write it mu naught into I into R square divided by 2 x square plus R square power 3 by 2. This is actually, this is a coil, then this at distance x from and radius R, B is given by this, and it's given actually this quantity is equal to 1/8 of B at center. So just simplifying it, mu naught I R square divided by 2 x square R square power 3 by 2, that is equal to mu naught into I divided by 2R and 1/8 of this. So mu naught I, let's get cancel, and 2 gets cancelled. This is 8R cube is equal to x square plus R square power 3 by 2. Simplifying it, we are getting x is equal to R root 3. That is the answer to question number 26, and that matches with option 2. Okay, next question number 27. A current I is uniformly distributed over the cross section of the long hollow cylindrical wire of radius R1. Okay, so we have like this, inner radius R1, outer radius R2, and current is uniformly distributed over this cross section here. So then we can write hollow cylindrical wire of radius inner R1 and outer radius R2. Magnetic field B varies with the distance R from the axis of the cylinder. So first thing is, we know by Ampere's law, B dot dl 2 pi R equal to mu naught into I enclosed. So if I take any point inside, then definitely I enclosed will be 0, so B will be 0. So we will get actually B up to small r is equal to R1, it will be 0. And after that it will like start varying, and actually if you just like you get B dot 2 pi, this is, I can write for R less than R1, we can write B is equal to 0, R less than R2 greater than R1. So for this case, B dot dl 2 pi R is equal to mu naught into I enclosed would be like I divided by, or let me write it, J multiplied by what? Multiplied by, this is I by pi R2 square minus pi R1 square into pi R square small r square minus pi r1 square. That will be like b, and simplifying we are getting it, actually it's not coming straight forward, like so it will be like starting from 0, it actually you can see r will be equal to 0, so it will be like or we can write r is equal to r1, it will be 0, so it will start from 0, but the graph will not be linear also, so it will match with either second and fourth, and here fourth one is linear, so it will be like most appropriate like this, and after that so we can write for r greater than r2, this will be like simply b dot 2 pi r is equal to mu naught into I enclosed, then b will be inversely proportional to 1 by r, so it will be this way. So option will match correctly with like answer will match with option 2. Question number 27. 28. 5 very long straight insulated wire are closely bound together to form a small cable. Current carried by the wire I1, I2, I3 and so on, negative current are in opposite direction. The magnetic field induction at the distance of 10 centimeter. So question number 28, we know actually by Ampere's law we can write B dot 2 pi r, B dot dl is equal to mu naught into I enclosed can be written total current, that is 20 plus I enclosed will be equal to 20 minus 6 plus 12 and minus 7 and plus 18. So simplifying it, and this comes B equal to mu naught by 2 pi into r is given as 10 centimeter, so it's 0.1 into this, simplifying, so it's 14 plus 12 20, I'm like 14 and 12 minus 7 it will be 5, so it's 19, and that it comes out to be 37, and if I multiply it by 2 divided by 2, then this is mu naught by 4 pi, so that will be like 10 to the power minus 7, and then simplifying it 0.1, so b is coming out to be 74 into 10 into 10 to the power minus 7, that is equal to b is equal to 74 micro, we will get Tesla. That will be the answer to problem number 28. Okay, next question number 29. So 3 long straight and parallel wire are arranged as shown in the figure. The force experienced by 10 centimeter length of wire Q. So force we can write F is equal to I L cross B. So we need, actually this is wire Q, so we need B due to R and plus B due to P. So B due to R will be like inward, this will be inward, and B due to this will be like, you can write outward. So we need to get net B equal to, I can write BR minus BQ, that is equal to mu naught into I divided by 2R, that is equal to 2 centimeter into 10 to the power minus 2, and minus mu naught into I is, I can write it's 20, and this is mu naught into I is 30 divided by 2 into R, that is 10 centimeter, so 10 into 10 to the power minus 2, this net B, and then it will be like what, net inward, so I can write L cross B, so the force on this will be like in this direction, net force, and force can be written as I, that is given as 10 into L, 10 to the power minus 2 into B net is this mu naught by into 20 divided by 4 into 10 to the power minus 2 minus mu naught into 30 divided by 2 into 10 to the power minus 1, and simplifying it, this simply we get F is equal to 1.4 into 10 to the power minus 4 Newton, and it will be towards right. So this is the answer, and which is matching with option 1. Question number 30. A current I flow through a thin wire shaped as regular polygon of n side, which can be inscribed in a circle of radius r. The magnetic field induction at the center of the polygon due to one side of the polygon. So this is actually equivalent to one side of the polygon. This is an n side, so this angle will be like this, total angle theta will be equal to 2 pi divided by n, and this 1 will be like theta 1 will be total theta by 2, so theta 1 can be written as pi by n. And we know actually if this is, and this distance is, let's say this is given as r, so this distance L can be written as what? R cos theta 1. Okay, and B, due to this I know actually this is what? Finite wire, so B is given by mu naught into I divided by it's 4 pi r into sine theta 1 plus sine theta 2, and both are equal, so we can write B is equal to mu naught into I sine theta 1 divided by 2 pi r, right? And r should be actually here equal to L. So just substituting the values, B we are getting mu naught into I, this is 2 pi r, this is sine theta 1 divided by cos theta 1, that will be tan theta 1, so B is equal to mu naught into I divided by 2 pi r, tan theta is pi by n. So this will be the answer to question number 13, which matches with mu naught into I by 2 pi r, tan pi by n, matches with option 3. Next question number 31. So a 1 meter long wire is moving right angle to the length with the velocity 10 meter per second. This is a 1 meter wire moving with 100 meter per second velocity. Length of the wire is 1 meter and perpendicular. The magnetic field of flux density B is given as 1 Tesla, and which is normal to the length of the wire if the direction of motion is inclined at an angle of 30 degree to the magnetic field, then induced EMF. Okay, so just let's see. So B is, I will say, inward, but the velocity is given in this manner. If I look at it from top, then B is in this direction. Okay, just try to look at it, and this will be the wire actually, and it's moving in this direction such that the angle between these two, B and this, is given as 30 degree. So for this I can write, it will be like B cos 30 degree, and this will be like B sine 30 degree. So only this will be the responsible for change in flux. Due to this, there will be no change in flux, no field lines are cut by this field line. So then EMF induced can be written as B only this BVL, that is B sine 30 degree into V into L, and just substituting the values, B is given as 1 sine 31 by 2 into velocity 100 into L is 1 meter. So we are getting EMF is equal to 50 volt. That matches with option 3. Okay. Okay, next question number 32. So here, two parallel wire carrying equal current in opposite direction are placed at x is equal to plus A and minus A. Let's say one wire, this is at minus A, another wire at x is equal to plus A, and if it is carrying current, this is carrying in this direction. Parallel to B, the magnetic field at origin is B1 and at okay, so this is B1, and at 2a comma 0 comma, so this will be at this point, it's B2. So first thing is magnetic field due to this will be inward, magnetic field due to this will be this is also inward, so B1 can be written as mu naught into I equal current. So this is also I, this is also I, and both fields are in same, so V1 can be mu naught into I by 2R. R is equal to A, this plus mu naught into I by 2A, so B1 is coming out to be mu naught into I by A. And B2, so magnetic field due to this will be inward 1, and magnetic field due to this will be outward, so another will be, so B2 can be written as mu naught into I by 2 into distance is 3A minus, you can write mu naught into I divided by 2 into A, Simplifying it, we are getting it B2 is equal to this is mu naught into I divided by 3a magnitude, and if I am just writing it in this way, then it will be this, but B2 need magnitude only, that can be written as B naught, mu naught into I by 3a. So now from here, just simply this is B1 divided by B2, that simply comes out to be 3. That is option number 1 matches with 1. Next question number 33. Two concentric coil, each of radius equal to 2 pi centimeter, placed at right angle to each other. Current 3 ampere, 4 ampere respectively are flowing through. So here, if one coil is like this, then another coil is like this, so that they are perpendicular actually, and radius is given as 2 pi centimeter. Current 3 ampere, 4 ampere respectively are flowing through the two coils. The magnetic induction in, so definitely they are at right angle, so magnetic field, like if I am taking it this way, then one this way, another will be like this way. So net B net will be equal to under root B1 square plus B2 square, and B we know actually it's given by mu naught into I by 2R. Is it? So B1 can be written as mu naught into I1, that is equal to 3 divided by 2R, and B2 is equal to mu naught into I, that is 4 divided by 2R. So B resultant is equal to under root this mu naught in by 2R multiplied by under root 3 square plus 4 square, that is equal to 5. So just simplifying it, mu naught divided by 2 into R is given as 2 pi 100 multiplied by what, 5, and this is 10 to the power minus like 7, so this is 10 to the power minus 5, so B is coming out to be 5 into 10 to the power minus 5 Tesla. That should be the answer, which matches with option 1. That is question number 33. Next question number 34. The magnetic field at the center of equilateral triangular loop offside 2L and carrying a current I is. So this is actually like here we will have this is a equilateral triangle, okay, like this, and its side is given as 2L, so means this will be L, this is 30-degree angle. I hope things are visible. I can make it little large also. Let me just draw it. So it's this situation in this. So first thing is this is given as L, this is 30-degree, then we can write this is equal to what, L by root 3 distance, and this angle 60-degree, this angle 60-degree, and current I, then magnetic field due to one wire B due to 1 can be written mu naught into I into sine theta or sine 60 divided by what, it's basically mu naught into I divided by 2 pi into this distance, I will say, let's say this is x, so 2 pi x, and B net will be equal to simply 3 times of B1. So B net, let me write it, this is mu naught I sine 30 root 3 by 2 divided by 2 pi, and x is given as L by root 3, so L multiplied by root 3, and B net multiplied by this 3 B1, so 3. Simplifying it, B naught, it comes out 3 into 3, it's 9, 2 into right, that's 4, yes, it's 9 mu naught into I divided by 4 pi L. That's the answer to question number 34, which matches with option 1. Okay, next question number 35. Let me erase the board. Okay, next question number 35. It's saying same current I is flowing in 3 infinitely long wire along positive X, Y, and Z direction. So this is the, let's say, condition X, Y, and Z. So current I, and I flowing in this direction, the magnetic field at a point 0 comma 0 comma minus a. So this is the point 0 comma 0 comma minus a, and here we need to find the magnetic field. First thing is magnetic field due to this will be 0 at this point. Magnetic field due to this we can write b, so it will be like this one, and magnetic field due to this it will be in this direction b. Yes, so we can get actually it's and b is given by magnitude mu naught into I divided by 2 pi into this distance, that is equal to a, and direction will be I j cap and minus I cap, and this will be the just answer which is matching with option j cap minus I cap mu naught into I by 2 pi a j cap minus I cap, which is matching with option 1. Next question number 36. Two infinite wire carry current I1 and I2 are lying along x and y axis as shown in the figure. Okay, so two wires, one carrying current I1, okay, this is carrying current I2, and another carrying current I1 placed along x and y axis like this. Locus of point where B is 0. So first thing is we need to check where B can be possibly 0. Actually, like what will happen, the magnitude are like will be okay equal, magnitude must be equal and the direction must be opposite because of these two. So first thing is here, due to this it will be like, you can imagine it will be like this cylindrical region, and due to this there will be this cylindrical region. So you can just imagine at this point there will be like this, is it, in this direction, and it will be like at this point it's coming outward. Due to this there will be possibility that it's coming inward. So we can say here there is possibility that field will be 0, and at if I just take different radius, then I will get exactly this will be the all locus of point where field will be 0 and like straight line. So here answer actually comes locus of point where B is 0 is a circle, definitely, because no other point will be there beside this, and locus of point where B is, I mean like point will be there, but it will be simply, we can write it, it will be two locus of this point where B will be 0 is a straight line. Next question number 37. A long cylindrical wire of radius A carries current I distributed uniformly over its cross section of the magnetic field. Okay, so first you need to understand this is a long cylinder of cross section radius A carries current I uniformly distributed over it. Now we need to consider 2 points. One is this small r, another is this which is capital R. So let's say B1 and B2. So then B1 is equal to what? Mu naught into I enclosed. I enclosed can be written I divided by pi into A square into pi into R square. This is I enclosed divided by 2 pi R. This is B1. B2 is equal to mu naught into I divided by pi A square into pi. I mean like it will be simply I enclosed for outside B2 point. So this divided by 2 pi R. And it's mentioned B1 and B2 are equal, so this implies mu naught into I, this is pi gets cancelled, and 1 r divided by pi and 2 a square. Just these two terms gets cancelled, 2 pi gets cancelled, a square is equal to capital R small r, a is coming out to be under root small r capital R. That matches with option number 2. Similarly, question number 38. Infinite long current carrying wire carrying current I, a charge of Q. Okay, so let's say this is an infinite current carrying wire carrying current I, and a charge of mass m and charge Q is projected with the speed v parallel to the direction of the current. Okay, let's say so from here Q, m and particle is projected with the speed v at the distance r from it. Alright, so magnetic field will be like inward at this, and B can be written as mu naught into I divided by 2 pi R. This is the B, and you can say B inward, so V cross B. So force will be like acting in this direction at this point of time. the distance from, then the radius of curvature at the point of projection. So first force can be written as, this is Q V cross B. So we can now, this is perpendicular, so this can be like Q V, and B is mu naught into I divided by 2 pi R. This should provide the required centripetal force, and I can write this is equal to m V square divided by rho is the radius of curvature, and it's asking like finding the radius of curvature. So rho can be written as 2 pi m V and into R divided by Q into mu naught into I, and which matches with option 2 pi R m V with 2. So that is answer to question number 38. Question number 39 here, two long wire, okay, two long wire carrying equal current I flowing in opposite direction, which of the arrow labeled A to D correctly represent the direction of the magnetic field due to the wire at point located at equal distance D from each other. So this is a straightforward simple question actually. The two wires, one carrying current outward, another carrying current inward, and due to this is the point where, so magnetic field due to this we can write it will be like at some right angle, so one component along this, another component, and similarly B at this is inward, this is like this, and this is inward, so it will be like perpendicular to this, and again two components, so we can just see these components will cancel out, net will be along this, so that matches with option, like that will be B, and 2 will be the right option. Next question number 40. A point charge is moving in clockwise direction in a circle with constant speed. Okay, so point charge is moving in clockwise direction in a circle with constant speed V. Consider the magnetic field produced by the charge at a fixed point P, not at the center of the circle, on the axis of the circle. So let's say it's then I need to consider this is the point P where magnetic field, and B is equal to mu naught into Biot-Savart law 4 pi R square. This is Q, this is V bar cross R cap. This is the Biot-Savart law, and now in this situation actually mu naught Q V and R cap, only what is happening here from this, actually this R cap is only changing, even R is remaining constant. So in this situation actually you can see only this component angle will be between, I mean like this R cap direction is changing, because charge particle is here, then R cap will be this, charge particle here, R cap will be this, is it? So because of that we can say even velocity vector is also changing, so that's why the direction of B will be changing, but magnitude wise everything is remaining constant. So that's why now it is asking the C, consider the magnetic field produced by the charge at a fixed point P, not at the center of the circle on the axis of the circle. Then it is constant in magnitude only, it's constant in direction definitely not constant in both, so it will be like only magnitude will be constant. Question number 41. Okay, so a particle is moving with velocity V is given as I cap plus 3 j cap, and it produces an electric field at a point given by E. So E, let's say the charge of the particle is E, then E can be written as 1 by 4 pi epsilon naught R square into, this is Q by this, or some R cap, right? And this is given as 2 K cap. So that is E for question number 40, 2 K cap. It will produce magnetic field at that point equal to all quantities are in. Okay, so now magnetic field can be written as B bar can be mu naught into Q V bar cross R cap divided by 4 pi epsilon naught into mu naught by 4 pi into R square, right? So just I need to substitute the values from here. It will be like direction, we just need to talk about like magnitude only, so this can be Then q by 4 pi epsilon naught r can be written as this 2 magnitude wise this, and it will be like electric field will be parallel to, you can write r cap. So cross r cap, then direction I need v bar cross r cap. So this first quantity, this quantity is equal to simply b bar is equal to mu naught, and this can be written as epsilon naught can be multiplied here. So this is mu naught epsilon naught into v is I cap plus 3j cap and cross 2k cap. Just simplifying it, we get it actually b is equal to I cross k, it's minus j, and j cross k, it's I. So mu naught epsilon naught 6 I cap minus I cross k, that's minus j, 2 j cap. This is the answer to question number 41, which matches with option 1. Next, question number 42. The flux linked with the circle is given by phi, the graph between the time x-axis and induced EMF. So first thing is phi is given as it's tq plus 3t minus 7. Then induced EMF is equal to minus d phi by dt, that will be minus t 3t square minus 3 equal, and this is the flux and like EMF induced. So definitely it will be a what? This is the EMF versus t. Graph will be a parabola. Straight line passing through origin, no. Straight line with positive intercept, straight line with negative intercept, parabola not through the origin. So that matches with option 4. Next, question number 43. Current I enter at A in a square loop of uniform resistance and leave at B. So this is the uniform resistance and it's entering here I and leaving here A. This is given as B, C and D. So I will be going this way, this way, this way, this way, and finally coming. If it is I, then I can write resistance is R, 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 R. So this current will be like basically higher resistance, current will be lower. So it's I by 4 and this current will be 3I by 4. Right? Then it's talking about this ratio of magnetic field at E. Okay, E is the center due to segment AB to that of DC. So mag B at E due to AB, that can be written as mu naught into I, 3I divided by mu naught by 4 pi into, like, because remaining things are remaining constant, so that will be like simply proportional to current, because distance, angle, everything is constant. So I can write B will be some let's say alpha multiplied by 3I by 4, and B at E due to CD will be equal to alpha multiplied by I by 4. So the ratio of BAB by BCD, we can get this comes out to be BAB by BCD. This is AB will be simply coming out to be 3. That is matching with option 3 also. Okay, next question number 44. Let me just erase. Okay, so next question number 44. A wire of length L is used to form a coil. So wire of length L is used to form a coil, let's say radius R. The magnetic field at its center for a given current in it is minimum. So first we know, let's say it has n number of turns, then I can write 2 pi R into n is equal to L. So first B is equal to mu naught into I divided by 2 into R, right, and into n. And now it's talking about B minimum. So B minimum will be like, it should be directly proportional to n, inversely proportional to R. So means for B to be minimum, n should be least and R should be greatest. And that's possible only when number of turns will be equal to simply there is only one turn. So that matches with simply one turn. Third is the right option for question number 44. 45. Square loop upside is rotating about its diagonal with velocity omega in a perpendicular magnetic field as shown in the figure. So here magnetic field is given, and this is it's rotated about this. So in this is standard result. Actually phi is given by BA into cos of omega t. Is it? Omega is the angular velocity. So now it's talking about what? All right, so if the number of turns in is n, so then it will be like n. Then magnetic flux linked with the loop at any instant can be written as, so phi can be written as n is given as tan b, and area will be like dimension is a, so area will be a square into cos of phi is equal to omega t. That will be the answer to question numbers, which matches with option 1. So this is all about complete paper DT07 for NEET part for like solution for part physics. I hope you understood, and that's all. Thank you to you.